Hi everyone, my name is Gavin and today I'm going to show you a reaction between potassium permanganate and glycerin. Over here I have a bottle of powdered potassium permanganate, and here I have a bottle of pure glycerin. When I mix these two together, they're going to produce a flame. So first what I do is I get a spoonful of potassium permanganate. I put this into my bowl. I've covered this bowl with aluminum foil so that when it starts to catch fire, it won't burn the bowl. I've also put a silicone pad on the bottom so it won't burn the table. What I'm doing right now is I'm creating a dent in the potassium permanganate powder for me to pour the glycerin into. Now that I'm done, I'm going to pour my glycerin right into there. So now I have to wait a while the reaction happens. What I think is really cool about this reaction is that we don't need a match or wood to start a fire. This mixture just suddenly combusts by itself after a while of staying stagnant. So now you can see the mixture is starting to smoke, and after that there's the fire. Wow, that was really interesting. To understand how that reaction occurred, we first need to learn about potassium permanganate and glycerin. Potassium permanganate is an inorganic ionic compound. It's actually a salt. As you might have guessed, potassium permanganate consists of a potassium and a permanganate. Potassium itself is just a neutral atom with one valence electron. Permanganate has one manganese atom in the middle, surrounded by 4 oxygens. Each of the oxygen forms a double bond with the manganese. When potassium and permanganate combine together, they form an ionic bond. Potassium loses its valence electron to one of the oxygens. Now that the oxygen has an extra electron, it doesn't need a double bond with the manganese to fulfill its 8 valence electrons. It only needs 1. The potassium is now positively charged since it lost an electron, and the permanganate is now negatively charged since it gained an electron. Now these two attract each other, forming an ionic bond. As we can see here, there's 1 potassium, 1 manganese, and 4 oxygens. So our chemical formula is KMnO4. As I had said before, potassium permanganate is actually a salt. In chemistry, a salt is defined to be an ionic compound, and when a salt is dissolved, it separates into its 2 ions. Potassium permanganate is a little different from table salt though. Table salt, when dissolved in water, is clear. Potassium permanganate, however, turns the water purple when it's dissolved. To see this, I'll get a little bit of this potassium permanganate powder. Now I'll put this into the water. As you can see here, this powder falls down through the water, and as it dissolves, it leaves behind a purple trail. Potassium permanganate has a wide variety of uses. In the medical industry, it can be used to treat athlete's foot, to cure dermatitis, and to treat wounds. It can also be used to treat water. For example, it's used to disinfect drinking water, it's used to remove iron hydrogen sulfide, and it can be used to remove small organisms from water treatment plants. Finally, potassium permanganate is useful in survival kits. Potassium permanganate, when mixed with glycerin or antifreeze, can start a fire. Potassium permanganate can also be used to write distress signals onto the snow. Now let's talk about glycerin. Glycerin is a colorless, odorless liquid. It has a high viscosity, which means that it doesn't flow as easily as some other liquids such as water. Glycerin is sweet and non-toxic, and it can be found at most local pharmacies. The chemical formula for glycerin is C3H8O3, and the structure looks like this. The central element of glycerin is carbon. There are 3 carbons in a glycerin molecule. Each carbon is surrounded by hydrogens and attached to 1 atom of oxygen. Each of the oxygens are also attached to 1 atom of hydrogen. Like potassium permanganate, glycerin also has a wide variety of uses. In the food industry, glycerin can be used to preserve foods to keep things moist, as a solvent, and as a sweetener. In the medical industry, glycerin can be used to lubricate and smoothen skin. Glycerin is also found in cough medicine, toothpaste, toothbrush, mouthwash, soap, and many other items. As I had said before, glycerin is a solvent, which means that many things can dissolve in it easily, oftentimes even better than in water or alcohol. Now that we know about potassium permanganate and glycerin, we can talk about oxidation, which is the chemical reaction that's going on right now. Oxidation can be defined in terms of oxygen transfer or electron transfer. So for clarity, I'm going to specify that everything I'm going to talk about is defined in terms of oxygen transfer. This part can get a little tricky, which is why I created a table for you. Oxidation is the process in which oxygen is added to a substance. This part is simple enough to understand. An oxidizer causes oxidation, which is also quite straightforward. However, this part gets a little bit tricky. An oxidizer actually loses an oxygen. At first, it might seem like an oxidizer gains an oxygen, but after we analyze it, we can find out how it loses an oxygen. I've created an example for you here, in which A is the oxidizer and B is the reducer. A gives an oxygen to B. So now we know that A is an oxidizer, so it causes oxidation. Now what does that mean? It means that it causes B to undergo oxidation. Since it causes B to undergo oxidation, by definition, it causes B to gain an oxygen. Since it causes B to gain an oxygen, that means A gave away an oxygen to B. Since it gave away the oxygen, that means it actually lost one. Reduction is the complementary reaction to oxidation. Reduction is the process in which oxygen is lost. A reducing agent causes reduction. These two, as before, are quite simple. But the reducing agent actually gains oxygen, and I'll go through this the same way I went through oxidation. We know that B is the reducer and A is the oxidizer. Since B is the reducing agent, it causes A to undergo reduction. That means that it causes A to lose an oxygen. Since A lost an oxygen, that means that B took away the oxygen from A, which means that the reducing agent actually gains an oxygen. Now we see that all of these definitions actually fit together. Oxidation and reduction reactions are complementary, so together they're known as oxidation-reduction reactions, or redox reactions for short. In our experiment over here, we have potassium permanganate as the oxidizer and glycerin as the reducer. This means that potassium permanganate loses an oxygen and gives it to glycerin, which is the reducing agent. We already know that potassium permanganate is soluble in many things, and glycerin can dissolve many substances. You can already start to put 2 and 2 together, right? This is our reaction equation for potassium permanganate and glycerin. On the top here we have our reactants. KMNO4 stands for potassium permanganate, and C3HAO3 is the formula for glycerin, as we already know. I didn't have room on the left over here, but I wrote out the products on the bottom. First, we have K2CO3, which is a type of white salt called potassium carbonate. We also have MnO2, which is manganese dioxide. Manganese dioxide is a type of black or a brown solid. Finally, we have CO2 and H2O, which most of you probably already recognize as carbon dioxide and water respectively. What this reaction equation tells us is that when we combine potassium permanganate and glycerin in these proportions, we get all of these products listed below in the proportions shown by the numbers. However, what this equation doesn't tell us is exactly how that reaction occurs, so I'll talk to you a little bit about that. you remember, first what I did is that I got some of this potassium permanganate powder and put it in a dish. Then I poured a few drops of glycerin onto that potassium permanganate. What happens after that is some of this potassium permanganate dissolves into the glycerin, separating into potassium and permanganate. Then our familiar oxidation reaction can occur. Oxidation happens between that permanganate and some of the glycerin. What happens is that the permanganate gives off 2 of its oxygens to glycerin, thus becoming manganese dioxide. This oxidation reaction releases a lot of heat, and if you'll remember from the clip at the beginning, you'll recall that this heat was large enough to cause the glycerin to start to boil. This boiling glycerin produced a flame that spread across the potassium permanganate, and this fire continued until the glycerin was fully consumed by the permanganate. Let's go back to this equation over here. We know that these numbers specify the proportions of the molecules. This is crucial because we know that chemical reactions aren't strong enough to break apart atoms themselves, and we also know that matter is always conserved. So this means that if we look at any type of element, there will be the same number in the side of the reactants and the side of the products. Let's take oxygen as an example. We have 14 molecules of potassium permanganate, each with 4 atoms of oxygen, giving us 14 times 4 atoms of oxygen. We have 3 molecules of glycerin, each with 3 atoms of oxygen, giving us 3 times 3. We can add these numbers together to find that there's 65 atoms of oxygen in the side of the reactants. We could do the same for the products over here. We have 7 molecules of potassium carbonate, giving us 7 times 3 equals 21 atoms of oxygen. We also have 14 molecules of manganese dioxide, each with 2 atoms of oxygen, giving us 14 times 2. We have 2 molecules of carbon dioxide, giving us 2 times 2 atoms of oxygen. Finally, we have water, which only carries 1 atom of oxygen, and there's 12 of those molecules. If we add these numbers together, we'll find that there's also 65 atoms of oxygen in the side of the products. This means that oxygen is balanced in our equation over here. If we did the same for any of the other elements in our equation, we would find that the number is also the same in the side of the products versus the side of the reactants. This means that the equation itself is also balanced. After analyzing all of those chemical reactions going on behind the scenes, one question stands out, which is why our mixture was stagnant for so long before spontaneously combusting. This has to do with our rate of reaction. In our experiment, the rate of reaction wasn't instant. One reason is that it takes time for the potassium permanganate to dissolve into the glycerin, and it takes time for the permanganate and the glycerin to go through oxidation. This is why we don't see a fire happen instantly. Another reason is that water was one of the products, and we know that water puts out fires. The only reason that a fire was able to start is because most of that water was carried away in the smoke prefacing the fire. There are a few ways to increase the rate of reaction. One way is to heat up the reactants before mixing them together. This makes sense because if the reactants have higher energy, they're more active and more likely to react with each other. Another method is to increase the contact surface area between the reactants. This also makes sense because if there's more reactants in touch with each other at any given time, there's more reactions that's going to be going on. I tried to do this by choosing powdered potassium permanganate because we know that smaller molecules have a larger relative surface area. In conclusion, today we first talked about potassium permanganate and glycerin. We discussed some of their properties and some of their useful applications. Then we learned about oxidation, which is the chemical process going on that allows us to see the fire. Afterwards, we saw the reaction equation for potassium permanganate and glycerin. We discussed what this reaction equation can tell us, but we also discussed what the equation couldn't tell us, which is some of the chemical processes going on behind the scene. Finally, we talked about the rate of reaction, which explains why the mixture was calm for some time before spontaneously combusting. Thanks for watching, everyone, and I hope you enjoyed my experiment.